Hello everyone and welcome back to another video. So today we'll be doing a Leetcode medium question which is about cloning the graph. So given a reference of a node in a connected undirected graph, we have to return a deep copy of the graph. And this is how the node will look like. So your whole integer which is its value, as well as its list of neighbors which will be nodes respectively, as you can see right here. So for the test case format, for simplicity's sake, each node's value is the same as the node's index. So for example, the first node will have a value of 1, the second node will have a value of 2, respectively. An adjacent C-list is a collection of unordered lists to represent the finite graph, and each list will describe the set of neighbors of a node in the graph. So for example, for this one right here, you have neighbors 2 and 3, and for this 4 right here, you also have neighbors of 1 and 3 respectively. And the given node will always be the first node with a value of 1, which is this one right here. You must return a copy of the given node as a reference to the clone graph. So what this means is that when I'm given the node, I cannot just simply return the node because there will not be a copy of the graph. And for example, if let's say I make a copy of the 1, so let's say the copy is right here, I also have to duplicate the copies of its neighbors as well, which is 2 and 4. Because if let's say I have the 1 here, and I set its neighbors to be the neighbors of this one right here, so it will just simply be pointing to the 2 and the 4 respectively. Because remember that these are objects, so they'll be pointed to. So what this means is that I probably need a method to create a new node. Okay, and when I take a look at this question, I guess one thing that comes to my mind is that I probably need a way for me to iterate through the whole graph so that I can take note of the vertices that are there as well as its edges. So a vertex will be the node, and the edge will be the connection between the two nodes. So I'll need an algorithm such that I can traverse through all the nodes and the edges. Okay, so we can probably use a searching algorithm such as BFS for us to explore the whole graph respectively via its vertices and its edges. So what I want to gain out of this is that firstly, I need to get the new nodes. And secondly, I also want to be able to know the neighbors of the nodes. So that eventually when I create all my new nodes, I can simply pair up the node and the node and the neighbors. But this time, the neighbors will not be the origin nodes, but instead it will be the new nodes. Okay, so what we can do is to probably use a queue system in this case. So initially we start off with 1, so I'll be appending the node 1 to the queue. Alright, and after that I'll be popping the 1 off. So I'll be getting the 1. And when I take a look at 1, I realize that it has connections to the node 2 and 4 respectively. So what I will do is to add 2 and 4 to the queue so that they will be ready to be popped up next. And when I iterate through that, I realize that I have to, and when I iterate through that, I will be able to generate a new node from this so that I'll have a new node with a value of 1. And I have to somehow have a way for me to be able to store this node. So what I will do is to use a dictionary or hash map in this case with a key value pair. So what the value will be the new generated node. And the key will be simply the value of the node. Because it's quite, as I mentioned before, the node's value will be the same as the index. Alright. And what I need to do is to also be able to take note of the neighbors that is connected to. So I see that it's connected to neighbors with a value of 2 and 4 respectively. So what I will do is to store them in an array. Because eventually my ultimate goal is that once I have finished going through and creating all my nodes and taking note of the neighbor values, I want to use these values right here to directly access my dictionary later. so that I can just simply form the connection with the nodes itself, the newly generated ones. So that will mean that I also have to use a dictionary or hash map for me to be able to store the array right here of the neighbor values. So as for the key value pair for this, the key will be the current node's value, and the value will be the array of its neighbor's values. If that makes sense. Okay, so hopefully everyone is still following right now, but if you are not that following, perhaps you can take a look at the coding solution so that it can perhaps look easier. So after this whole thing is done, right, all I have to do is to just take a look. Okay, maybe let me just clean this up first. Or maybe just clean this up first. This part. So as I iterate through the whole graph, firstly what I will get is a dictionary with the key being the value of the node and the value being the new node. And I also achieve another dictionary where the key is the value of the node and the dictionary is the array of the neighbor values. So what I will do is to iterate through this dictionary. And as I iterate through the dictionary, what I can do is that firstly I can get the value, right? Because it's the key. And the node is the node I can access it using the key, the value of the key. And for the value of the node, it's also the same as the one in the other dictionary right here. And with that, I can access the array of the neighbor values. So for example, when I first access the value of 1, with this dictionary right here, I can get back the node 1. And when I use the 1 right here, with this dictionary right here, I will get back 2 and 4, which is an integer of array values. So using this array, what I can do is to iterate through the array, and then I can use all these values right here to access the newly generated node in this dictionary. So that with that being the case, I can set up the neighbors to be the one in the newly generated nodes right here. So using 2, I can access the newly generated node at 2, and using 4, I can access the newly generated node at 4 respectively. So what I can do in this case is that I will be able to create another array of neighbors of 2 and 4. But this time, these neighbors are the newly generated ones, and no longer the ones in the original node, because I've already created them. And then I simply have to set this node's neighbors to be this array right here, and I will have successfully set up the neighbors. So after iterating through all this, you are already given that the given node will always be the first node with the value of 1. So after all this iteration, what I can do is to simply return from this dictionary right here. We can just simply return 1. So with that being said, let's move on to the coding part of the solution. So let's take a look at the coding solution right now. As always, let's start with some pseudocode first. So first, let's take a look at the variables that we will need. So first up, it will be a dictionary for us to hold the key value pairs of the newly generated nodes. We also need a dictionary for us to be able to hold the array of the neighbor values. And lastly, we will need a queue system for us to be able to engage in the breadth search for us to be able to search through the whole graph. Okay, so what I will do now is to first I will define a method for me to generate a new node. So define generate new node of node. So what I will simply do in this case is to just simply generate a new node with a value and with no neighbors at the start. So I'll just simply create a new node with the node's value and an empty and no neighbors, and I'll simply return the new node. So what this function does right here is to help me to generate the new node so that it's not just the node itself, but instead it's actually a copy of the node. Okay, so let me just bring this down here first. And next up, let's define our variables. So let's just call it new nodes to hold our dictionary of generated values, or neighbor values, to hold the array of the neighbor values, and lastly a queue, which I'll be using an array. Okay, so let's first handle the trivial case whereby we are given an empty graph to begin with. Because I can see right here, inside this example tree is a very trivial example whereby we are given an empty graph. So if the node is none, then you can just simply return output empty right here, which is just what I stated. But if it's not, then let's continue and take a look at the pseudocode. So if node is not empty, what we'll do is to append the node to the queue. Okay, then while the queue is not empty, what we'll do is to get the first value, or get the node which has the first index, the latest first index, because I'll be popping off from the front. And then after that, so actually I missed stop in my explanation just now, but what we also want to prevent is that when we take a look at 1, then it sees that it has a neighbor of 2, and you take a look at 2, it sees that it has a neighbor of 1, and keep going back and forth respectively. So we want to prevent that, because if not, it will cause a time limit exceeded issue. So first we have to check if it's a key inside our new nodes, because if it's already a key, then that will mean that we have already visited the node. So if the key is inside the node, if the value is a key in new nodes, then we simply do nothing, because it has already been traversed. Else, what we have to do is to take a look, is to firstly generate the new node. Okay, and once we have generated the new node, we store it in our new nodes dictionary, with the key being the value and the value being the node, the new node. Okay, and once that is done, we have to iterate through the neighbors. And as we iterate through the neighbors, we'll get hold of the value and add it to a temporary neighbors variable, perhaps. And then after that, with that array, we'll store it inside our all neighbor values right here, which is a dictionary. So the key will be the value as well, value of the node, the current node, and the value will be the array of all its neighbors' integer values, because we'll be using the neighbors' integer values to be able to access the new nodes later. So once we have iterated through this part of the code, we will be able to get a dictionary of new nodes and a dictionary of all the neighbor values respectively. So after that, what we have to do is to iterate through the keys in my new nodes. Okay, so the value of new nodes, I will be able to get back the new node, and using the same key of at all neighbor values, I'll be able to get back the array of neighbors. And then after that, I'll iterate through the array of neighbors and use the values there to access new nodes. This will be how I'll be able to access the newly generated nodes to become my new neighbors. And after I have set the neighbors to the new nodes, then I'll just simply return new nodes 1. Because like what the question says, the given node will always be the first node with a value of 1. Okay, so if that sounds good, then let's start coding up now. Okay, so if node is not none, then I'll add it to the queue. And let's settle this while part first. So while queue is not empty, then I'll get the first node using the pop method. Then what I'll do is to check if the current node's value is not in the new nodes. When it's not inside, then I'll continue this algorithm. So I'll generate the new node. Let me see what I defined there. Okay. Of the current node. And then I'll set it to my dictionary will be the new node. After that, I'll iterate through the array. So current node neighbors is equal to current node dot. Okay, maybe let's just write this more succinctly. So for neighbor in current node neighbors, first I'll append them to the queue. Because I want to visit them later. And after that, I will have to get hold of the value. Neighbor value will be the neighbor.value. So what this means is that I should probably create a temporary neighbor array first. Then I'll simply append it to the temporary value. And once I iterate through all these, then I can add it to my all neighbor values dictionary right here. So remember the key will be the current node value, and I'll assign it to temp neighbor values. So with that being said, what this will do now is to get me all the values respectively. So once I iterate through this, then I can come down to this final stage right here. So for num in new nodes, which will be the key, then I can access the new node that I have. And then I can access the array of integers using the same key when accessing all neighbor values right here. All neighbor values of num. So take note that these are still integers. So what I have to do is to iterate through them. So let's just use another variable, maybe x. First, I have to get hold of the node. So maybe 1/3 node equals to new nodes of x. So this will be how I actually get the new node that I created. And I guess what this means is that I have to create another temporary variable to store all these new nodes right here. So temporary array will be, I'll be appending the 1/3 node to it, because that will be the neighbor of the new node. And once all that is done, what I can do is to simply, because this is the actual node that I'm looking at now, right? So new node.neighbor, I'll just simply set it to the temporary array. And finally, what I get from this is that I'll be able to get the neighbors, but this time the neighbors are actually the new nodes. So after this is done, I can just simply return the node at index 1, because that will be the one that is always given. And with that being said, I guess this is how the overall code will look like. So let's take a look at the time space complexity. So time complexity wise, I believe that it will be an O of V plus E, where V is the number of vertices or nodes, and E is the number of edges or the number of connections we have in the graph. For the space complexity wise, it will also be O of V plus E as well, because I'm using two dictionaries right here for me to hold all the vertices and all the neighbors respectively. So yeah, I guess this is how the overall solution will work, and I believe it should work. Okay, I just want to highlight some minor stuff that I did. So actually, if the node is none, what the question wants us is to return none actually, instead of the previous answer that I put here, which is an empty list. And also I made a slight typo right here. So initially my code was neighbor, but based on the question itself, we are supposed to access neighbors instead. So I missed out the S right here. So yeah, with that being said, the code should work right now. Overall, as you can see, the solution does work. And if you have any questions, then feel free to leave them in the comments down below. So yeah, thanks for watching and see you pretty soon, I guess.